Hello, this is Dave from Dimensional Consulting. Today we are going to talk about datums, datum feature simulators, and simulated datums. In this video, we will discuss feature of size datums. The drawing has datum feature symbols indicating that the back surface of the part is datum feature A, the left hole is datum feature B, and the width of the slot is datum feature C. We will focus on datum feature B. Datum feature B is an imperfect hole. It is theoretically perpendicular to datum feature A, but it will never be exactly perpendicular to datum feature A. To make a measurement, we place datum feature A on the surface of the datum feature simulator. A gauge pin, which is imperfect, but almost perfect, protrudes through datum feature B. Another gauge pin protrudes through datum feature C. Simulated datum axis B is the axis of the gauge pin that goes through datum feature B. Simulated datum plane C is a plane that goes through the axes of both of the gauge pins. Datum feature A will contact simulated datum A on at least 3 points. Since datum features B and C are referenced max material boundary, datum features B and C may or may not contact the gauge pins. Since the position tolerance is MMC, there is a fixed size gauge pin that protrudes through the middle hole. The hole may or may not contact the gauge pin. In the theoretical world, exactly the same size and shape as the datum feature simulator is the true geometric counterpart. It is perfect and theoretical. Therefore, it doesn't really exist, but it is very important. The surface of the true geometric counterpart is datum A. Datum B is the axis of the theoretical pin that goes through datum feature B. Datum C is the plane that goes through the axes of the theoretical pins. Perpendicular to datums A and C and through datum axis B is one more plane. Together, they establish the datum reference frame. The datum reference frame provides an origin and direction for the basic dimensions that locate the tolerance zone. Here, the origin for the basic dimension of 15 is at datum axis B, as the three mutually perpendicular planes establish the datum reference frame. Understanding what these terms are and how they relate to each other is fundamental to understanding how parts are dimensioned and measured. We start with what we see on a drawing. The drawing references a physical part. When we get to the measurement world, we talk in terms of what happens in the physical world and what happens in a theoretical world. On the drawing, we specify feature control frames. They exist only on the drawing. The feature control frames specify datum features. Datum features exist on the physical part. Datum features constrain the translations and rotations of the part. When we move into the measurement world, first consider what happens in the physical world. The physical part is placed on a physical gauge. The gauge is called a datum feature simulator. Datums derived from datum feature simulators are called simulated datums. These might be physical surfaces on the gauge that get touched by a CMM probe, or they might be axes or center planes that are derived from pins or holes or slots that are part of the gauge. Now step into the theoretical world. The true geometric counterpart is the same size and shape as the datum feature simulator. The only difference is that the datum feature simulator is real and the true geometric counterpart is theoretical. From the true geometric counterpart, we derive datums. They are points, lines, planes, or combinations thereof. They are theoretical. Datums are used to establish datum reference frames. A datum reference frame is three mutually perpendicular planes. The datum reference frame establishes directions and origins for basic dimensions. The basic dimensions are then used to locate tolerance zones. That's today's video. If you want to see more tips like this, please subscribe. And visit my website at dimensionalconsulting.com.